My study, obviously, is using classification and regression tree valley bottom modeling techniques to identify riparian vegetation in Pinal County, Arizona. Jumping right in, looking at the why, an overview of Pinal County, the current state of riparian data sets, the project objective, the model development for the CART and valley bottom models, model results, determinations of riparian zones using a density analysis, conclusions review, and questions. This was done with the Land and Water Trusts. I was a participant with the Pinal Partnership Open Space and Trails Committee on the Natural Watercourses and Protection Subcommittee, who is trying to advocate for better riparian protection in Pinal County. And the first step to that is identifying what is riparian. This is Pinal County, just north of us. We've got about 5,300 square miles of area, so reasonably large. Most of the citizenry is out here with the agriculture in the west. Those are the major cities, Florence being the capital. About 390,000 people, and elevations ranging from about 6,400 feet on the slopes near Mount Lemmon down to 981 feet out where the Gila River exits the county in the northwest. All in all, there's 8,358 miles of watercourses as identified by the National Hydrology Dataset in the county. The two major ones are the San Pedro and the Gila, but there are a lot more than that. So that's kind of what we're trying to look at. This is what the riparian zones in the county look like right now. There's four major data sets covering the county: the National Wetlands Inventory, the State Wildlife Action Plan, the Regional Riparian Mapping Project, and the Southwest Regional Gap Analysis. The coverage for these generally looks at perennial streams and or riparian areas that have obligate or preferential riparian species. So leaves out most of the rest of the county, which is ephemeral or light intermittent. So my objective was to provide a comprehensive assessment of the presence and distribution of riparian zones across Pinal County using remote sensing imagery and topographic data. And I wanted to identify these zones into zero riparian, mesoriparian, and hydroriparian areas, which is a common schema used in neighboring counties. Get to those a little bit later. The classification method I used is called a CART model, which is classification and regression tree. It is a supervised classification technique, so you identify classes beforehand. It's a dichotomous tree approach. It's non-parametric, meaning it makes no assumptions. It can use other data besides spectral, and it's recursive. It looks kind of like this. This is just a very small subset where it just takes a value at a single band that it determines, and then makes a split, and then recursively splits down the tree. And it can use each variable more than once to get to these nodes, which is where the classes end up being. I picked out 10 classes for the entire county, which is a pretty heavy simplification, but the two major ones I was concerned about are the bottom there, the annual and perennial vegetation. I used about 1,500 total training points for the model that I extracted the values from, with half of that being used as a control to test the other half against. I want to talk about precipitation real quick. This is from the PRISM data sets. This is the annual average over a 30-year period for the entire county. So it's pretty variable with some really dry and then the mountainous regions getting a lot more precipitation. June, on the other hand, is much less variable, which is important because most of my imagery was from June, and I was looking at annual and perennial vegetation, so I didn't want any localized green up confusing my data sets. Pretty small standard deviation, 2 millimeters. These are my training points for the CART model. Wanted to use a randomized distribution, so I'd place them randomly using ARC and then go to each point and then reassociate it to the actual class it was supposed to be at. For the model, I used 26 total variable layers, 3 topographic, 16 spectral, 5 vegetation indices, and 1 temporal. Not a lot to say there. The spectral mostly came from the NAPE imagery, which I Tried to blur out a little bit using low pass and 10 by 10 meter focal mean, because I wanted to reduce mixed pixel problems when you've got something like this that might cover a whole canopy of a tree. Real quick, looking at the NAPE data, these are the collection dates for the NAPE imagery. Because it's aerial photography, not satellite, it's collected in flight paths. And so you don't get, the images aren't taken at the same time every day or on the same day. All these different days have different times as well. And so it confuses some of the values. One of the issues I had was shadowing, which became an issue out in the east, where there's more mountains, and the shadows are all pointing different directions, which makes it a little more difficult if my model wanted to use topographic data. So I used a NOAA calculation from extracting the time values to determine aspect or azimuth and elevation of the sun, and then reran the hillshade on that, and then mosaiced them together, which produced a hillshade that looked like that. And so you can see the variability is pretty large. The darker areas being early or later in the day when the sun is at a lower elevation, pretty much. The valley bottom model uses topographic data, to create a probability raster for the existence of valley bottoms. Valley bottoms being associated to riparian areas where potential riparian vegetation could grow. This is critical because my CART model didn't differentiate between vegetation types other than perennial and annual. The training variables used for the valley bottom model were elevation, Euclidean distance, slope, Euclidean distance by slope, height above the channel, a compound topographic wetness index, a topographic position index, and then a Z value for the topographic position index, which use a 100-meter kernel around each cell to determine those. And then the training points used are just binary, so it's valley bottom or not valley bottom. And so I went about and dropped about 830 in transects like that across what I identified as valley bottoms. The model works by extracting the values at the training points to the variables, and then tries to fit them to a logic equation, where these beta values represent the closest the fit along the logic function that it can find. And so then it kicks out this logic equation that's run through the raster calculator to produce the probability image, which has values from 0 being not very probable to 1, which is very probable. I had to breeze over quite a bit, but this is kind of what the model looks like, or most of the data processing. The inputs being the NAPE collection grid, DEM, 6 of those, 2 Landsat images, and then 412 NAPE images that had to get mosaic together. That all gets processed and then put into the 2 models, where some things happen a little under the surface there, and then a little more processing, and then I get my vegetation zones, which I'll talk about. This is all divided up into the blue being spectral data, or the light blue being spectral, gray, which kind of looks dark blue, being topographic, vector data, classified raster. Yellow is a calculation done outside of GIS, so it's something I had to port into Excel or something else to get an equation out of. The CART confusion matrix kind of looks like this. The overall accuracy was only at 76%, the kappa at 0.78, but most of that variability comes from these non-vegetated classes over here. If you think about the size of Pinal County, it's about 17 or 13 billion pixels, and trying to associate those 13 billion pixels into 10 classes causes gross oversimplification because you're looking at materials, not just a coverage area like a Landsat image or something like that. So, but I was pretty happy with the values I got out here. 85 is kind of your target range for a CART tree like this, 85%, excuse me. The classified image that it kicked out looks like this, which is pretty good. What you kind of expect, obviously some misclassification out here, where it's looking at probably some barren or maybe herbaceous areas that's it's looking at are light impervious, so not ideal. But obviously the vegetation shows up pretty, or the agriculture shows up pretty strongly, and then you've got your more boreal forests in the mountains showing up right there, and then of course the riparian areas along San Pedro and the Gila there. The percentages of land cover look kind of like this, which is fairly what you expect. Water's a little high Looking at the imagery, there was some confusion between shadows and water because you're getting 0 values out of both. So, but I didn't concern myself with that too much. Annuals, perennials, looking right about there, which is pretty reasonable. The valley bottom model probability layer looked like this, which isn't real helpful, but I had to go through and look at individual areas across the county and then assess what the most likely probability was for valley bottoms across the whole county. I determined that a 0.62 or 62% probability was reflective of the most of the county. So it looks more like this, which is a little hard to see because here we are at 90,000 feet or something. But I just used that then to clip the classification down to. And then I wanted to process the data that was in these valley bottoms to the riparian classes. 0 riparian is pretty much upland areas, except it's in greater densities than you would see in the upland areas. They're a mixture of preferential, facultative, and non-riparian plants. Mesoriparian is kind of the middle ground. It's a mixture of obligate, preferential, and facultative, and then the hydroriparian is basically obligate and preferential, which is where you'd see like cottonwoods and stuff like that. So, and then that, I wanted to perform a density assessment on that to determine what sort of area was in that. And I did that in a 1/3 acre area, about a 0.3 of an acre. Did a density analysis for each classification, annuals and perennials, and then use them together to identify the zones. And so I picked these values for annual upland, annual upland, annual 0 riparian, meso, hydro, perennial, and then like that. And so it looked at the, it didn't have to be annuals first, it could have been vice versa, but it was arbitrary. Looked at the pixel, determined what class it fell in the annuals, and then from there matched it up with the perennials, and then kicked out a classification. And then I clipped that to the valley bottoms, or that's the identified vegetation zones across the whole county. Clip that to the valley bottoms, and it looks like that. Predominantly 0 riparian, which is what you'd expect. Obviously, agriculture is still getting identified there, but I can just clip that out pretty easily with a vector, so I'm not too worried about that. And then down on the San Pedro, you're getting a lot of hydro, which is pretty good, and a lot of meso, kind of in these mid regions here, kind of at the middle elevations. At a closer level, just it's 3 different areas across the county. The valley bottom model has trouble with unconfined areas such as floodplains, so it's underrepresenting along San Pedro here. Which isn't terrible. I can just match that up with some FEMA floodplain maps, and that'll resolve sort of that issues. But pretty good results in the kind of upland areas that we're avoiding classification in the other studies. So pretty happy about that. In conclusion, the combination of both models provided a much more comprehensive data set of riparian areas in Pinal County. This could get revised continually to provide a better assessment, a more accurate assessment if you wanted to. And then you could also apply this to successive years of imagery to produce a change analysis if you wanted to. Just to review, the existing data sets underrepresented riparian areas in Pinal County. I used remotely sensed spectral and topographic data in a classification and regression tree model to classify land areas. The topographic model was used to map valley bottoms. Vegetation classes or zones were identified from the classes of the CART model and then clipped to the valley bottom model where probability was at 62%. Use software in here, ARC, GRASS I had to use for the flow accumulation because ARC has a limit on its DEM size it'll process for flow accumulation, and GRASS also will do a multi-directional flow, which ARC can't do. So it just does a single directional flow. So that was an issue. PyScripter, obviously, with some Python. AirDOS and C5 was used to generate the CART tree, and then Excel for some other knickknacks.